Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. Today we will present about the structural characterization of organometallic compound. My name is Wahadah Binti Ghazali and I will be the first presenter. Our next presenter is Salwani Binti Razimi and our last presenter is Solehah Binti Samsudin. Let's proceed to our presentation. There are two types of donation in carbonyl bonding, which is sigma donation and also pi-back donation. Sigma donation occur from highest occupied molecular orbital of carbon monoxide to empty metal orbital of the correct symmetry. Sigma donation causes a synergistic effect where the donation makes the metal more electron rich, thus it willing to do back donation. For the pi-back donation, the donation occur from the filled metal orbital to the lowest unoccupied molecular orbital of carbon monoxide, which is the pi star. The synergistic effect of this back donation is that it maintains the electron density on carbon, thus preventing excessive negative charge on metal. The similarities of sigma and pi-back bonding is that both bonding are cooperative. These carbonyl bonding are also applied to other pi-acceptant ligand other than carbon monoxide. There are two net effects of carbonyl bonding on carbon monoxide. Firstly, the electron density are removed from the weak sigma bonding. Next is, there is an increase of electron density at strong anti-bonding sigma star level. The process in carbonyl bonding causes the MC bonding to become shorter and stronger than the normal single bond. They also causes the CO bond in carbon monoxide to become weaker and longer than the normal triple bond. The process of carbonyl bonding can be proven through IR spectroscopy. By considering the Planck equation shows that the stronger the bond, the higher the stretching frequency. By looking at the table of example of three different metals with the same ligand of carbon monoxide, we can see that vanadium hexacarbonyl has metal with the smallest nuclear charge. This proves that vanadium has a weak ability to attract electrons, and it has great tendency to back-donate electron density to carbon monoxide. The consequences of this event are, firstly, there are high electron density at pi star lowest unoccupied molecular orbital. Next is, it will reduce the bond order and the bond strength of carbon monoxide. And lastly, it will lower the frequency of carbon monoxide on IR spectrum.
So, I will continue for my part. When the charge on the organometallic species is more negative, the tendency of the metal to donate back the electron to the pi star LUMO of CO become greater. Metal tend to donate more electron back to the CO, make the pi back bonding stronger. It will also result to stronger and shorter of CM bond. As we know, the stronger the bond, the higher the frequency and the energy of the CM stretching vibration. But opposite to CO bond, when CM bond stronger, CO bond become weaker. So the frequency and the energy of the CO stretching vibration become lower. Next, this slide is the summary for CO bond. free CO is where uncombined and unattached of CO bond with any metal. There is no pi back bonding occur from metal to pi star of LUMO CO. Free CO is the strongest and shortest bond, result to highest energy and stretching frequency, but lowest in wavelength. Consider the Planck's equation, which is E equal to hv, also equal to hc over lambda. So while for bridging metal, CO attached or combined to any metal, highest degree of pi back bonding occur from metal to CO. CO receive electron from metal and make the CO bond become weaker and longer. So that is why for bridging metal, CO bond has the lowest energy and stretching frequency, but highest of wavelength. Next is for alkyne bonding. For this slide, we want to know what the effect on the C double bond C bond of ethene when sigma and pi back donation occur. For sigma donation, the ligand of CC bond will donate its electron to the metal. From this donation, it removes the electron density from the CC pi bonding HOMO, while for pi back donation, the electron from the metal is donated back to the CC ligand, and from this donation, it places the electron density in the CC pi star LUMO. So both donation, sigma and pi back donation, lower the CC bond of alkyne. Next, the greater the electron density of the metal, the greater the degree of pi back bonding to CO, which is MC bond, becomes stronger, and the lower the energy of the CO stretching vibration. This corresponds to the lowering of CO bond strength as a result of lowering of CO bond order by populating the LUMO, which is an antibonding molecular orbital, pi star.
Hi, so in the last part of the topic, I will explain about how the organometallic complexes are observed in IR and carbon-13 NMR spectroscopy. In organometallic complexes, you may find several numbers of isomer structure. That's why, as you can see from the diagram above, there are two different IR spectrum, which represents, the first one represents you the trans isomers, and the second one represents cis isomers. So in IR spectroscopy, compounds with more than one carbonyl ligands usually will have more than one IR active carbonyl bands. The bands means the inverted peak from the diagram. So each stretching bands correspond to the linear combinations of stretching and compressions of the carbonyl bonds. Theoretically, the number of carbonyl bands cannot exceed the actual number of carbonyl. Next, in the slide next to me, it shows you the list of IR active modes for some carbonyl complexes. So this table you can refer to if you want to predict the organometallic complex structure. If you are given with the chemical formula for sure. Next, in the slide next to me, it shows you the list of IR active modes for some carbonyl complexes. So you can refer to this table if you want to predict the organometallic complex while you have been given the chemical formula. Number 3 from the table, it is MCO4L2. So this complex have two isomers, which is trans and cis. So okay, first take a look at the trans isomer. It has two ligands, right? So the structure is symmetry because the environment is same, because you can cancel out it at the symmetrical line. So it will produce single peak since it has the same environment. Meanwhile, for the cis isomer, it is asymmetrically bonded, so you can cancel it out. It is non-linear. That's why it produces 3 or 4 individual peak in the IR spectrum. Besides IR spectroscopy, we also have carbon-13 NMR spectroscopy. However, this type of spectroscopy has a natural isotopic abundance of only about 1.1%, which is very low. But you can still refer to this table if you want to predict the type of ligand based on the chemical shift appeared. Okay, we can combine the IR spectroscopy and carbon-13 NMR spectroscopy. Let's take a look at one example. As you can see at the slide, a complex with the formula of CO5CrC5H7N was prepared. So it is obviously an organometallic complex. So the detail is the IR in the carbonyl region, they are stretches at 2057, 1980 and 1908 cm95. Meanwhile, for the carbon-13 NMR, the shift assignable to CO is 216 and 223. So explain the observation. Okay, let's take a look at the solution. The compound has 5 CO, therefore it is likely to be an octahedral with 5 positions occupied by CO and 1 position occupied with another ligand, C5H7N. Yes, correctly. If you properly look at the structure, there are 5 CO attached to the CR and another 1 ligand attached to CR. Next point, for MCO5L, it is expected that there are 2 or 3 IR bands, which agrees with 3 stretches observed. Okay, in relate with the statement, we found 3 stretching bands, right? So, if we look back at the table, we can see the MCO5L are expected to have 2 or 3 IR bands as well. So it is confirmed that the structure belongs to this one. And the third point, there are 2 types of CO, which is equatorial and axial, which can be assigned to the carbon-13 signals at 216 and 223. So this one resembles to this, the CO and this CO symmetrical, meanwhile this one and this one as symmetrical as well. So they exhibits 2 peak in carbon-13 NMR spectroscopy. Okay, I think that's all from us. As usual, thanks for watching.